means through this, so I found side tools, and it does unit conversions. So you can use, basically I found the exponents in here.
There's a hole in the sphere. That he escapes the sphere with it.
Yeah, so April 1st is like very funny, but I really don't find it funny if somebody hacks into my Piazza account and posts this. So this is unacceptable. So whoever did this, please come forward, because this is I usually have a good sense of humor, but this is like, beyond this. Okay, so whoever did this, please come to me. All right. Welcome. EE123, lecture 127. Woo! That was a joke.
Okay.
You hacked yourself?
That guy. Very heavy. We were having a good time with that. Oh my god. Apparently buried. Oh my god. That was very well done.
Gotta leverage something over something, otherwise it's not funny. All right.
We felt bad for you. We hate you.
All right, my second favorite lecture, because it's the second one in the same topic. We're just getting better. So I thought it was funny. People were posting, and I was like, delete. Changing comments. That was hilarious.
Wait, it's left? Is part 2 actually do that?
Which one? No, actually, that was true. Yeah. I think Frank was a little bit away this week, and when he replied that, no, just a minute, it was a little bit not updated. Okay, so after this comic relief, okay, so we were talking about last time about what were we talking about? Compressive samples. Okay, compressive sampling. So compressive sampling, the idea we talked about the idea of having redundancy, having compressibility. How does this help us? Redundancy, compressibility allows us to denoise, it allows us to compress, reduce the amount of data, but how does it lead us to making fewer measurements? And so if you look at the Shannon-Nyquist theorem of sampling band limited signals, it is sampling signals, any type of signals. It's the worst case scenario. These are serious people. They take things really seriously. You don't want to mess with them. So they look at the worst case scenario. But as I said before, when we try to make measurements of something, it's usually something and not anything. And when you want to make something, maybe you can come up with an idea of reducing the amount of samples and then still be able to reconstruct. So the concept of compressive sampling integrates the sensing, the compression, and the processing within the same concept. Okay? And let's now go through and look at what actually making measurements really means. So I'm not going to go from analog to digital conversion. What we're going to look at today is the case of you've got an unknown vector unknown vector, and you're allowed to make linear measurements of that vector. Okay, so everything that we're going to talk today is going to be in the discrete domain. So let's say you've got a signal in Rn, and you want to be able to measure it, right? So according to the principle of linear algebra, if you have n unknowns, you need to make at least n measurements in order to be able to get your signal. And so this would be the type of a matrix that a desktop scanner or a camera would then sense. Who's taken 16A? You're not there yet, right? It's like next year is going to be the cohort of 16A. Okay. So in 16A we have a lab, which it's called a single pixel camera, in which you go and you have a projector and an image that you want to create an image of, and you have one solar cell, and you measure the voltage on the solar cell, and what you do is project bright light on a single position in the image, measure the solar cell, project another bright light on a different part of the image, and so on and so forth, and just scan this bright light. And the reflected light really represent this type of a matrix. So each one of those pixels are evaluated, and this is what we store. Okay? So this is a sensing matrix, the identity matrix of a desktop scanner, a camera, in the ideal case, without, of course, cropping the high frequencies and things like that. Okay? So in the ideal case. Okay, that's great. But any idea of other sensing matrices? I want to evaluate what are the values here. What do I need to make in order to be able to get that? Identity is great. It's fantastic. What else? Any invertible matrix, right? Anything that is invertible, so any type of linear measurement that have n independent measurements will be enough in order to be able to reconstruct it, right? So then you can think of all sorts of trade-offs. For example, if I only measure the identity and I measure basically one pixel, if you think about it like one time point, then this is not really an efficient also type of sampling in the sense that I don't spend a lot of time measuring that pixel. So maybe noise is not, from a noise point of view, it's not great. I can think of another one. Here's this one, Fourier, the Fourier kernel. This is just the real part of the Fourier, okay? But it has also a complex part. So a Fourier matrix or a DCT, right? That will be another way of sense that particular vector. And in fact, this is how we sense information in MR. So in MRI, this is the sensing matrix, a Fourier measurement. So we need to make n linear measurement. I can also think of arbitrary sensing, like you mentioned before. So something that has n linear independent measurements that will give you, you'll be able to recover your signal. So in that case, a good sensing matrix is the best one. So you said n, like invertible. Invertible is not probably the best one in the sense that maybe some measurements are going to be less, more noisy than other ones. The one that's orthogonal is really a good matrix. And how do you measure orthogonality? If you take this sensing matrix and you look at and you do an inner product between each row and if you take an inner product between each vector column or actually row vector, it doesn't matter, then you would see that those are air bears go away. They said they're going to, get rid of air bears, so just get rid of it. Great. me just get rid of it. Okay. So if you take the inner product between each column and row with the other ones, you'll see that each one of them is orthogonal. If you're not taking the inner product with it yourself, then the inner product would be 0. Okay. So any row and column here will be orthogonal to each other, except, of course, the same row. In which case, you get the identity matrix. So another way to think about it is phi transpose phi, or phi transpose conjugate phi, would be the identity matrix. Okay? This is linear measurements. And obviously a linear reconstruction, because it only requires you to invert this matrix and be able to reconstruct your signal. Questions? Boring. We've seen this before. Can you move on? Right? I'm speaking for you. Did I take a picture already? Yeah. You see this? It's called old age. Is where you don't remember anymore. Short-term memory loss. Okay, so in compressed sensing now, the situation is going to be different. Different in a sense that now we're going to make, if we have a signal which is length is n, we're not going to make n linear independent measurements. What we're going to make is we're going to make m linear measurements. Okay. M, which is less than n. So the sensing matrix is going to be fat. Fat sensing matrix means that it's an underdetermined system of equations. We have less equations than unknown. But we're also going to assume that there is redundancy. There is sparsity in our signal. And hence that vector, while its length is n, is going to have k non-zero coefficient. It's going to be k sparse. Okay, so it's going to have k values which are non-zero, and the rest n minus k values are going to be completely zero. That's the assumptions that we're going to make. Okay. So we're going to make this, and the number of measurements we're going to make is somewhere between k and n. Okay, it's less than n and slightly larger than k. Okay. That is the situation. And we're going to make incoherent linear projections. Now, you're being incoherent right now, Mickey. What do you even mean by incoherent? Right? We're going to talk about this. But for example, one of the arguments for incoherency would be that this, let's say this matrix, is generated, for example, by picking values out of a random Gaussian distribution. Okay? Just an example. Okay. So as it turns out, a good compressed sensing matrix is the one that's incoherent, which means that if you actually do the same trick of taking phi transpose conjugate times phi, it can never be an identity, right? Because this is obviously a lower rank than n. So it cannot be the identity. The rank of this matrix is determined by m. So if the rank of the matrix is determined by m, and m is less than n, and you have an n by n matrix, it cannot be an identity. But it is approximately orthogonal, and this is approximately the identity. That means that if I look at phi transpose phi, I'm going to have very large diagonal, and I'm going to have very low off-diagonal elements. as low as I can. Does this make sense? Now, why can this not be identity? Because if this was an identity, it means that its rank is going to be n, and it cannot be n, it can only be m. Because it's made out of this outer product. Okay? And as it turns out, if you've got this property of incoherence, it will preserve information of sparse signals. If your signal is sparse, then it will preserve its information with some probability. And it turns out that probability is what they call in the field overwhelming, that it's very unlikely that it will not be preserved. But now it's not a definite solution, as you will see. So the Nyquist criteria tells you you can absolutely reconstruct whatever it is. In compressed sensing, the situation is, on average, you'll be able to reconstruct. There are going to be some cases which are fundamentally broken that you will not be. But the probability for those will be extremely, extremely small. Okay? So just remember these concepts of incoherency, which means that the matrix is approximately orthogonal. That means that what it really means is, when the sensing matrix is approximately orthogonal, that basically means that each one of the columns, each one of the row in this matrix, right, the one that we actually use to make measurements, gives you significant additional information to the other ones. Okay? That's what basically it means. It's maximally trying to give you the most out of it. And each one of the columns here, while they cannot be orthogonal to each other, they're as orthogonal as it can be. Okay? Very, very little inner product between each one of these columns. That's basically what it means. Okay, so let's say you have a sparse vector, and let's say now you've got this matrix. And so now you've got a system of equations, right? You've got y equals phi times x. This is an underdetermined system of equations, and you want to find x. Okay? You want to find x. Okay, so now let's say I know where the non-zeros are in x. Can I reconstruct? Can I be able to recover x? Most likely. The reason is because I'm going to have now 1, 2, 3, 4, 5, 6, 7, 8 number of measurements, and I'm going to have 1, 2, 3, 4 unknowns. Right? If I knew exactly where x is, I can remove the columns that are irrelevant, that they basically multiply 0. And I'm going to have an 8 by 4 matrix, which is going to be actually thin, multiplying a 4-length vector, which I don't know what it is. Right? So if I knew where the non-zeros are, then I know I'm going to get a good solution. But this is not the case, and this is what is really... So this is the case of band-limited signals. Right? You know where things are. I know that my spectrum is concentrated at a particular frequency. If I know that, then that's not a problem. I can design a certain sampling with lower rate that will make sure that there's no aliasing. This is how if you can also think about this concept. So if I knew where the non-zeros are, then that's not a problem. But I don't know where they are. And my model is, I've got sparsity, but I don't, so just a few number of coefficients, but I really don't know where. They could be anywhere. On one hand, kind of limiting because I have less information than the band-limited case. But in some other way, it's a much nicer model in the sense that it allows for way more type of signals to be able to represent through this model. Band-limited only tells you I've got, frequencies, here, and here, and here. That's it. That's band-limited. But now, sparsity tells you, well, I don't care where you organize as long as you're a few. It's much more powerful, much more representative or natural signals. Okay? So, potentially, if I don't know where they are, there's really no hope of how to find them. Like, how would I even go about it? Right? But my hope is that because X is sparse, has reduced degrees of freedom, can I use these reduced degrees of freedom in order to constrain my reconstruction such that, or my solving of the system of equation, such that I'll be able to reconstruct it. Okay? So that's my hope. Okay, so what the first thing that people do? The thing that people do is says, okay, you know what? Among all possible solution, I'm going to find the one with minimum energy. Right? Because, I have sparse signals, there's less energy, right? Like it cannot occupy everywhere, right? So why people use this solution? Do you know why? It's actually quite interesting. It's human behavior. Let's say you need to get to the 5th floor. Okay? You know that if you walk up, it will improve your health over, the long run. Right? But then most of you probably take the elevator. Why? Even though it's not always faster. Like this elevator, come on. Like you not get there faster, right? Right. It's like it's easy. Like it's there, it will take me up. So I'll just use it. Okay? Right. So the way people would have originally addressed it is they say, okay, among all possible solutions that satisfy this equality, infinite number of them. Infinite. Because I've got so much degrees of freedom. I can pick anything in the null space of this matrix, and it would still fit. Right? Among all possible solutions, I'm going to look for the one that has the smallest energy. You know what's cool about this? As I said before, it's easy. You know why? Because this is least squares. It's called least norm, but yeah, there's a closed form solution, the Moore-Penrose inverse, very simple, closed form, done. One tiny, tiny issue. You know what's the tiny issue? It's wrong. As it turns out, you're most likely not to get what you started with. Your ability to reconstruct your original signal, if you do this, if it's sparse, is going to 0. Okay? It's not going to be able to reconstruct it. So that's a shame, right? Because I got like this nice closed form solution. It's going to give me a single one. It's great, but it's obviously wrong. And then you can ask, what you can ask me questions about. Like, try to ask a question, like intelligent one. That encourages a lot of dialogue here. Right, not intelligent one, like a stupid. Ask a stupid question. Oh, why is it wrong? Right? That's actually intelligent. Why is it wrong? Right? We'll get to this. I'll give you an intuition why it's actually going to be completely wrong. Okay. Yeah.
How wrong is it?
Quite wrong.
How many of the entries different?
Unbelievably amount of them. Most, if you increase the dimensionality, most likely all of them will be wrong. It's a good question. Depends on the problem, but yeah, they could be really different. Any idea actually how to solve this? Like the original one, if you know that X is sparse? How?
I don't think you need all the columns in the matrix.
Right, but I don't know which. Chicken and egg. Yeah.
Why can't we just probabilistically remove some of them, check if the answer changes, and then I can remove some of the columns. If the y output doesn't change, it means that x was 0.
But there's infinite number of solutions.
And there's a number of solutions, but like say I'm just looking at phi, I randomly remove a column. If my answer to y doesn't change, that means that
Well, I can find any X that will get to Y. I mean, like it's just like there's infinite number of solutions. I can give you the same Y, even if I remove a few of them.
no, that's not my point. I'm now determining where the zeros are located by doing this method.
How?
If I remove a column and then the output, so
Yeah, but you can remove a column corresponding to this guy, still get the right solution. Like still get the same Y. Like you can find a solution that will do that. Dang it, right? Come on, give me some ideas. Well, maybe there were just one non-zero, right? Maybe there's just one. Yeah? Let's go and try. Let's just try all possible of one non-zero coefficients and see if we can get a fit. Can we? Probably not. Right? All right. Then, how about we try with 2? All possible combinations and then solve these least square problems. Like, to find whether we can get the exact one, right? All possible 2 combinations. And then all possible 3 combinations. And if I did all possible 4 combinations, I will land on a solution. Right? So I can solve a combinatorial problem and maybe find a solution. Now the question whether the solution is right? Whether the sparse solution is. And as it turns out, if I minimize the L0 norm, which is the cardinality, basically the sparsity, number of non-zero coefficients that satisfies this, under the conditions of certain amount of sparsity, certain amount of incoherence of phi, there are results about that can be quantified, you can say that you can guarantee that you will find the solution. Not for every phi, but for certain phis that are incoherent. Under some sparsity assumption and on some m and k and n, combination of these will give you the right solution. Okay, so there are theorems that says for a certain incoherence with certain sparsity k, with an m that is some function of that k and n, you'll be able to guarantee reconstruction with overwhelming probability. Okay? So these are the results that they have in this area. We're not going to go too much into this because just from your background. But I just want to give you kind of the concept. Yeah. So we could do that. We could go and try all of them, and under those assumptions of sparsity, coherency, we'll be able to find a solution. Now, what's the problem? It's non-convex.
So it's going to have it's a hard problem to solve.
It's a hard problem to solve. It's a combinatorial problem. We cannot just use descent methods in order to solve it. We'll have to really try everything to be guaranteed that we go through all these solutions. And that's terrible. This is really disappointing. Okay? But one of the most exciting results in this area is that So as it turns out, here you basically need k log n. I think just k number of measurements in order to do this. Just need k number of measurements in order to be able to solve that. So m equals k under some incoherency assumptions. Okay. As it turns out, if you're willing to trade off a little bit and do m equals k log n, number of measurements, then if you solve this problem, you minimize not the cardinality or the L0 norm and not the 2 norm, which is the energy of x. But among all possible solutions, you find the solution that has the least L1 norm. Do you know what L1 norm is? Take 127. 127, take it, please. Don't forget that. If you ever learn something with this class, is that you should take 127. Just add 4. You'll be done. Okay. The L1 norm. L1 norm is the sum of absolute value of a vector. It's also called the Manhattan distance, because you're only allowed to go in blocks, on a grid. You're not allowed to go on a 2 norm, which is a diagonal, right? If I have a vector like you're there, and I want to get to you in a field, let's say in the oval, I can go straight to you. So this is a 2 norm. The distance is Euclidean distance. But in Manhattan, I'll have to use the L1 norm, which is going up, whatever avenue, and then turn right to the street and then get to you. So it's the sum of absolute value of your coordinates. So if you solve this problem, which turns out to be a linear program that is very efficient, they're an extremely efficient solution to this, you'll be able, and you made m equals k log n, that's much, much less than n number of measurements, and this is incoherence, and so on and so forth. With overwhelming probability, you'll be able to solve the solution of x that is equivalent to solving the cardinality, the non-convex problem. Right? Give me something hard, I relax the problem, I change it completely. But then I still solve the same solution. Unbelievable. Right? It's crazy. Think about it. You have this super hard problem, you change it, but to make something easy, and that something easy has the same solution as the hard problem. Insane. Huge impact on lots of fields. Take 127 if you want to know how to solve it. Now here's some arguments, geometrical arguments of why is this the case. Okay. If we think of the domain of sparse signals in R3, what are the domains of sparse signals? Are these sparse signals in R3? That's the most sparse I can figure out, right? Except 0, right? So 0, 3, 0 is sparse in R3. That means that it lies on an axis. That's basically what sparse means. It lies on an axis. And what is too sparse in R3? It's one of these planes, right? Either this one or this one. So it's either on an axis or on one of these planes that intersect these axes. Okay. So these are the domains of sparse signals. So they can't be everywhere. That's your redundancy. That's where the degrees of freedoms are reduced. Okay, so now let's say I'm going to make one measurement of this vector. I want to find this vector. I don't know what it is. I have a way to observe it. I make a projection. Okay, I take an inner product with some other vector. Okay, so what does it give me? If I know that inner product, what do I not know? Like where my solution could be. Now my solution is somewhere in 3D. If I take one projection, where is my solution? It was before it was 3D, after I took one projection and I know the value of the projection, in 2 dimensions, which is a plane that is periodic, that is orthogonal to the vector that I measured, all right? Yep. Geometry. Okay? So now I know my solution lies in this plane. I made this vector. This is y. I know now that x1, x2, x3 live in this plane. They don't live anywhere else. But the solution is this one. Okay? So now let's minimize, find among all possible solutions the one that has an minimum L1 or minimum L2. Minimum ball or minimum ball. One is called the L1 ball, which you really don't want to catch. And the L2 ball is just like a normal ball. But the L1 ball, if I throw it at you, just duck. Because if you catch it, you're going to get holes in your head. Because it's spiky and pointy. Okay, it's a terrible ball for playing, but it's a great ball for solving sparse equations. Okay? So what does it mean to solve the minimum L1 ball? What the minimum L1. So among all possible solutions, I'm going to take an L1 ball and I'm going to inflate it till it hits the plane. When it hits the plane, that's the minimum L1 ball, right? That's the minimum L1, right? So I'm going to put a ball in the middle and till it hits the plane, okay? L1 ball spiky. This is how the L1 ball. That's all the places in 3D space that have exactly the same L1 value. It's spiky. It's always most likely going to hit. It's going to hit on one of these edges. There are, in this case, 1, 2, 3, 4, 5, 6, 7, 8 possible other solutions that will hit on a vertex. But among all possible 3D, options, just 8 of them could maybe land you on a vertex. But all the other ones will basically intersect with one of these axes. Okay? So that's where probability comes in. So it's really unlikely for you to pick a plane that exactly aligns with a vertex. Right? That's unlikely. Okay, now let's take a normal ball and then right? If you inflate a ball that's rounded, where it's going to intersect? What are the chances of it intersecting with the axes? 8 out of infinite. Right? Out of infinite possible planes that you picked in order to do the projection, 8 of them are not good solutions. Otherwise, 8 of them are good solutions. Otherwise, you're not going to get a sparse solution. Okay? So this almost always gives you sparse solutions. Whether they're right or not, that's a good question. But it's going to give you a sparse solution. This one is likely not to give you a sparse solution. The reason is L2 gives a lot of penalty for large values, and it prefers lots of small values to one large value. Right? One large value is squared, high penalty. So lots of small values is better. Okay? L1, the cost of having one large value is not as big as having lots of small ones, because they just not add in square. And that's one of the other reasons that there's another argument for why you get sparse solutions. Okay? Does it make sense? Take 127 if you want to know how to solve it. Okay, so here's the kind of a nonlinear linear sampling theorem in this case. Because first of all, minimizing the L1 norm is nonlinear. Okay, like you minimize a nonlinear function. So a nonlinear sampling theorem. So in the case for Fourier sampling, or band-limited signals, this is the Nyquist one. You've got some signal that is supported in a set in Fourier, right? That's the Shannon-Nyquist theorem, right? And then Shannon says, well, the set is known and connected, and it has a certain size. And so you can get exact recovery from that size of equispace times samples. And then you do a linear reconstruction by a sinc interpolation, if you do Nyquist theorem, for band-limited signals. For this case of compressive sampling, this is a nonlinear sampling theorem, that basically your set is arbitrary. It's unknown, but it has a certain size. It's not necessarily connected. And then you can get exact recovery from B log n, almost arbitrary place samples. So it has to have this incoherency associated with it. And the reconstruction is done by nonlinear reconstruction by convex programming, as opposed to just doing a sinc linear interpolation. Okay, so that's the difference. So here's a question. Where can I use it? How practical is this? Is it even practical? I mean, it's exciting, but is it practical? In what situation, what type of systems, these fees that satisfy these properties can actually be used in practice? And so the question is really, can you create this incoherent system that's used in practice? And I would argue, yes, there are. I wouldn't say infinite amount of them, but there are some very useful systems. And here's an example. Fourier matrix, this is just, again, the real part. If you randomly remove rows in the Fourier matrix, basically you don't evaluate certain Fourier coefficients. That's basically what it means. If you take that matrix, okay, so remove all the zeros here, and so now you've got yourself that kind of a matrix. If you look at its inner product between every column and other column, then it would be approximately orthogonal. So the off-diagonal element are going to be low. Now, it's not as low as you think, but as you increase actually the size, then they're actually getting lower and lower. And what's exciting, I would say, for me, is that in MRI, we sample in the frequency domain. We sample using these matrices. We have control which Fourier samples to acquire. And so that makes it maybe exciting if we can reduce the number of measurements and still be able to reconstruct images. And an MRI is often very slow in acquisition and is limited by the encoding time, so how much time it takes to acquire all these Fourier measurements. And you acquire them one at a time. So that's what makes it exciting. Okay, so there's this recipe for compressed sensing. Okay, this is a manual Candes that I tried to draw. It's pretty good, but close. The glasses, at least. Okay, so there's a recipe here. One thing in this recipe that needs to come is the sparsity or compressibility. Okay, so yes, we're talking about k-sparse vectors, but if you can represent them using k-sparse wavelet coefficients, that's also k-sparse vectors. Before the phi, you just put a wavelet transform matrix. Now your phi is phi times wavelet transform matrix. You need to make sure that this is still incoherent. Okay, but if it is, then you got yourself a good result. If phi is random Gaussian entries, then it's always true. It's uniformly good. But those are not necessarily practical type of systems. Sometimes they are. Okay. In the case of Fourier sampling, you need to do some pseudo-random, non-uniform sampling of the frequency domain. You can actually not sample uniformly the frequency domain. If you do sample uniformly, it sucks. That's one of the worst things that you could do. So you want to sample non-uniformly, randomly in the frequency domain. And then you need to do some nonlinear reconstruction, something that enforces sparsity. L1 norm enforces sparsity, but there's actually other ways of enforcing sparsity. Now I'm going to try to give you an intuitive example of compressed sensing when we're talking about one-dimensional signals. Okay. So let's say we're looking at a situation where I have a signal which has a sparse spectrum. Okay, signal with a sparse spectrum. Sparse spectrum means that this signal is composed out of a linear combination of these complex exponentials, which I'm showing actually just the real part of them, and I'm showing them overlaid, but of course they're added. Okay? So this has a sparse spectrum. Okay. So what if I measure in time, right? I measure that signal in time. How many samples I need to, like at what rate I need to sample those, the signal in order to be able to recover this? What is the rate? And I would say, according to Nyquist, like I need to sample this uniformly and at the Nyquist rate, twice the bandwidth. If I do that, see, he's a serious guy, right? Like you don't want to mess with him. If you do that, then you compute a Fourier transform, and then you got yourself your signal, right? If you take an infinite number of measurements over time, but at a certain rate. If you cut them, then you got yourself ripple, and basically sinks, right? Remember that. So that's the difference between discrete part and not discrete part. But if you think about this as an operation of resampling, so if I have a vector that's already sampled and now I need to make measurements, then if I just compute the Fourier transform of the vector, and if I know that its DFT is this, then it would still be the same DFT because it's just I took the inverse DFT and I computed the DFT back again. It's no problem. Okay. What if I subsample that sequence? I use an equispace subsampling, which is sub-Nyquist. What would happen then? You go sub-Nyquist. Boop, 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 boop. Right? You go sub-Nyquist. And now you get your first order. Because we're below the Nyquist. So if you subsample, you got yourself replicas. Your signal's being replicated. Right? That we know this. We know this from... Yeah, we do. From class. But here's the problem is, even though you have sparse signals, look, but in the case for sparse signals, they actually might not overlap on top of each other. They might, but they might not overlap on top of each other. But still, even if they don't overlap on top of each other, there's still ambiguity, because if now I look at my signal, it could have come from numerous places. Each one of these replicas are equally likely to be a solution. Let's say I know that it's 3 sparse. Which one? And what if the case where there is overlapping, then there's really an ambiguity? Okay, so there's inherent ambiguity in the reconstruction. I can just not do it. Okay, I can't recover those. So that's a problem. Okay, so I did mention that what happens if you do non-uniform sampling. Let's try to do non-uniform sampling. In non-uniform sampling, if I compute non-uniformly sample measurements of that sequence and take a Fourier transform, then I will still get this aliasing or this wrapping of frequency on top of each other. But now, it's not going to be coherent. It's going to look like that. So how would you go about, and if it's incoherent, how would you go about to recover then the signal? So if you've got a sparse signal, and you've got something that is now has an interference that's incoherent, then maybe there's a chance for you to recover that signal. This is John Pauly. It's my PhD advisor. It's Dave Donahoe. It's my other PhD advisor. That's a pretty good one, actually. He actually looks like this. Okay, so I'm kind of running out of time, but I just want to give you some kind of intuition of what's going on, and then we continue next time. Actually, after the midterm on Monday, right? Okay. All right. So if I randomly subsample, I'm going to get this incoherent. So what you're going to see is you're going to see that basically the situation is going to be the following. You're going to see some of your signals, and it's going to be corrupted by this interference. Now, the interference has to be below that signal. And the reason it has to be below the highest signal is because it's generated by that signal. If I have only one spike has a uniform, one frequency is basically a complex exponential in the time domain. If I randomly subsample a complex exponential, I basically have a random sequence. And I compute a Fourier transform of it. What we'll have is a peak because it has some DC component, and then it will have interference on it. Okay? But it's generated. It's what's called a point spread function. Okay? You take one peak, compute an inverse Fourier transform, multiply by some mask, which is like filtering in the frequency domain. So it's a convolution with the inverse Fourier transform of the sampling pattern. So it's generated by this. Okay? So what you're going to see some of these elements above that interference, and some that are small are going to be buried in it. Okay? Now, while this looks like noise, it's not really a noise. It's generated by these. But here's the cool thing about it. The cool thing about it is that, first of all, that interference is completely computable. You can compute it. You can take a spike, inverse Fourier transform, multiply by a certain mask, take a forward Fourier transform, and then you know what that contribution is. Okay? Computable. Okay? So that's one thing. And it's always lower than the largest component. Now, this looks like noise. It's not really noise, but it looks like noise. We know how to the noise sparse signals. We set a threshold. Right? So what you could do is you could set a threshold. So will be a contribution of this component. This will be a contribution of this component. And this will be a contribution of this component. It's pretty nice, huh? Yeah. Ooh. So here's how you actually recover. What you do is you say, okay, I can calculate what that interference is.